이 양자 컴퓨터 하는 사람들은 참 기발한 방법들을 잘 생각해내는 것 같아요.
그러니까 요게 맨 처음에 어떻게 발견된지는 저도 자세히 모르겠는데요. 아마 뭔가 이게, 그러니까 제가 주워들은 바로는 이게 퀀텀 워학에서 나오는 퀀텀 워학 알고리즘에서 쓰이는 테크닉이 있는데, 그거가 어떻게 여기로 들어오게 돼가지고
음,
만들어졌다고 그러더라고요. 네,
음.
그 시작은 어떻게 처음에 이걸 어떻게 생겼는지는 잘 모르겠어요, 사실.
퀀텀 워크라는 거는 뭐 양자 컴퓨터와 관계없이 또 옛날부터 있었을 거고요.
근데 그거를 좀 알고리즘 연구하는 사람들이 퀀텀 워크를 연구를 많이 하긴 했어요. 왜냐면 좀
음,
토이 프로블럼이긴 한데 익스포넨셜 스피드업이 있는 경우가 있거든요. 그러니까 퀀텀
음,
워크이 똑같은 형태의 클래시컬 워크에 비해, 랜덤 워크에 비해서 그냥. 네.
음. 퀀텀 워크에서도 플럭츄에이션 디스퍼션 티오럼 그런 게, 근데 거기 온도란 개념이 없으니까 없을라나? 뭔가 비슷한 게 있을 것 같은데 거기.
글쎄요. 기본적으로 이거는 랜덤 코인 대신에 그냥 그 확률이 2분의 1이면 그거 대신에 그냥 헤더멀드 오퍼레이션을 가고 이러는 차이여가지고 온도라는 개념은 좀 없을 것 같긴 해요. 제가 알기로는.
이건 무작위가 아니군요.
네.
음,
유니타릭이죠. 네. 음.
음, 음. 오케이, 예, 시작할까요?
네. Okay, so let's continue. Before I begin the second lecture, I do want to spend a little bit of time talking more about select and prepare, because I only told you about what they do. I didn't really tell you how they are implemented and what the costs are. So I think it's good to at least talk about a little bit about that. And more specifically, I will talk about select mostly because prepare, it's a slightly more complicated story. Okay, so I will just show you the simplest possible implementation of select. So let's say let's start with a simple case. Let's say I have two Pauli, P1 and P2. In that case, clearly I only need a single extra qubit to apply the select operation. So 0 psi applied to select, be this thing, and 1 psi state will be mapped to this state. And importantly, so P1 and P2, it'll be a general like n qubit Pauli operator. Okay, so it could be a very highly non-local operator. And one way to implement this is the following. So what you would do is that you have, let's say, let's call the first register as S. Okay, and this is the S register. Okay, and what you would do is the following. So let's see. So when let's see. So if S is in the 1 state, then we want to apply P2. And if S is in the 0 state, then we want to apply P1. Actually, maybe. Okay. So I'll actually consider the second case first. All right, so so what you do here is the following. So if S is in the 0 state, then it does nothing so far. And if it's in the 1 state, then you first flip this qubit from 0 to 1 state, okay? And then if that qubit is flipped to 1, then it applies this P2 as desired. And then what you do is that you want to, so you can think of the second register as an extra register that stores intermediate computation. So if you think about what we learned in the first few lectures, we talked about this uncomputation. So what we're doing is that we're simply doing the uncomputation on this part. So after you apply the C0 operation, the second register is back to the 0 state. So you effectively, if this S is in the 1 state, then you applied P2. And then now, what you want to do is doing something similar, but you just change the value of the input bit. So what you would do is that you apply the X operation. And do something that looks very similar, except applying a controlled P2, you apply a controlled P1. So if you want, what I would want to do, what I want you to do is to compare this part and that part. So they look very similar, and they are they have a similar role, but slightly differently. So this is basically applying P2 if, actually only if S is equal to 1. And this is applying P1 only if S is equal to 0. So this way, in the second stage, if the S is in the 1 state, you do nothing. So the thing that you end up doing is still just effectively only P2. In the second stage, if you're in the 0 state, then you end up applying P1. So this is something as desired. So more generally, you have P1, P2, Pn. And in that case, things will look very similar. The only difference is really the size of this S register. So you still have this S, and it'll be consisting of log2n qubits. You still have this extra intermediate computation layer, computation register, which stores whether this S is in a particular state or not. And you have this another thing, which is whose input is an arbitrary state psi. And in between these pieces, you have maybe let's call them as, sorry, this is not working well. Maybe x1, x1, x2, and et cetera, et cetera. And different stages will be broken down to when, so that this will be the case where you apply P1 only if S is all zero state. And this will be the part where you apply P2 only if S is all zero except the very last thing is one state, and et cetera, and et cetera. So in total, all of these operations can be broken down into total of n stages. And each different stages, they look very similar to each other. And their cost is also very similar to each other. Because the only difference between, let's say, this part and this part is the precise x1 or x2 that we're applying. And these are just single qubit Pauli operators, which are extremely cheap operations. So if you have n different Paulis that you have to apply, then that amounts to basically having order n basically log n gates. And you can be a little bit more smarter about this, and then you can reduce this to actually order n gates. So in the context of the Hamiltonian simulation, what this means is that if you have more terms in the Hamiltonian or in the Taylor expansion, as in our case, then it'll be more difficult. The complexity of implementing the select operation will increase. So for instance, if you compare a very simple Hamiltonian like a Fermi-Hubbard model to a complicated quantum chemistry Hamiltonian with long-range Coulomb interactions, even though the computational cost will be polynomial in both cases, the cost for simulating more complicated looking Hamiltonian will be larger because the cost of select will be larger. And similarly, also for the prepare, if the Hamiltonian is more complicated, then the cost of repair is also more compared to a simpler Hamiltonian. So just wanted to put this out there. Are there any questions about this?
Is any of these schemes implemented in the actual quantum computer, like the Google computer or whatever?
As far as I know, the answer is no. Actually, I don't see any difficulty in implementing them, but on their own, they're not particularly useful. Only by using them many times, they become useful. So maybe that's why people haven't really done it.
Okay.
Okay. All right. So, right. So what I want to discuss in the remainder of this lecture is this last point. So we haven't discussed how to boost this probability. All we've established so far is that with some sequence of operations followed by a measurement, we can apply certain operator probabilistically. So it would be great if we can somehow apply this deterministically. So I'll tell you about a general technique behind this called, it's not exactly amplitude amplification, but it will be useful to talk about the amplitude amplification first. So there's a very well-known quantum algorithm called Grover's algorithm. You might have heard about it. It's an algorithm to search a particular element from a database and compare it to a classical algorithm, which scales linearly with the size of the database. Grover's algorithm only scales like a square root of the size of the database. And there's a generalization of that, which is known as amplitude amplification. And the idea behind this is very simple. So I want to tell you what this is about. So the basic setup is the following. So suppose you begin with some quantum state, let's say all 0 states. So here 0 is really all 0 state over, let's say, n qubits. And the thing that we want to do is we want to amplify the amplitude of this particular state psi. So without loss of generality, we're assuming that this 0 state can be written down as a linear combination of psi state and its some state that is orthogonal to that. And what is given to us are 2 unitary operations. One is this R0, which is basically a phase operation. It gives a phase of -1 if you're in the state 0, and it gives you a trivial phase otherwise. And the other operation is similar to R0, except that instead of applying a phase only to the 0 state, you're applying a phase to this psi state. So the question is, given these 2 sets of two operations, can we somehow amplify the amplitude of this psi over here? And the answer is yes. And I'll tell you roughly how this works. So the intuition behind this is the following. Well, first of all, what is important to note is that when you apply these operations, R0 and R psi, to this subspace spanned by psi and psi orthogonal, then you always remain in this subspace. Okay, so why is that? So if you apply, let's say, R psi to psi, that's clearly minus psi. And if you apply R psi to psi perpendicular, then that's obviously R the perpendicular. And what about this thing? So what about that? Well, remember, R is I minus this thing. So without loss of generality, we can, well, actually, we can just use the expression for 0 to say that. So if we apply this R0 to this state, then we get this. And that's, of course, equal to that. And of course, 0 is a linear combination of psi and psi perpendicular. So we're still in the 2-dimensional subspace. And you can perform a similar calculation for R0 applied to psi perpendicular. Again, showing that this is a linear combination of psi and psi perpendicular. So effectively, when we apply R0 and R psi, we are always in a 2-dimensional subspace. And because these 2 vectors, psi and psi perpendicular, are orthogonal to each other, we can and their amplitudes are always real. We can write this down. We can express the state of the system on this plane. So I'll do that. So these two axes, they correspond to these two different states. And viewed this way, we can interpret this R0 and R psi geometrically. So what is R psi? So suppose we have an arbitrary vector. Like this. Maybe I'll call it as V. Okay. Then what if you apply R psi? Well, we're basically looking at the psi component of this vector and applying a minus sign to that. So pictorially, the vector that is shown on the left will transform in this way. This is a reflection. What about R0? So if we go back above and look at this expression, 0 is, again, in the span of psi and psi perpendicular, and it's some vector which can be with an angle of theta between itself and psi. So this is the 0 state. And R0 is just a reflection with respect to this 0 vector. So we have this psi here. What you're just doing is that you're reflecting, let's see, you're reflecting along the direction of 0. So the vector that you're going to get will be something like this. Okay, and it's a well-known fact that in 2 dimensions, if you have 2 reflections, the composition of those 2 reflections is always a rotation. And you can verify, well, actually, you can verify that in this case, if you apply R0 and R psi applied to the state, what you get is actually cosine 2 say theta psi plus sine 2 theta psi perpendicular. And you can apply this n times to, n minus 1 times to get cosine n theta psi plus sine 2 theta psi perpendicular. So in this sense, if you start with a superposition of this, if you start with some quantum state, where in the desired state that you want to get is psi, you can, and if you can somehow detect that state, you can sort of boost this amplification, boost this amplitude. And this is known as the amplitude amplification technique in quantum computing.
Wait, so you basically you change, you go from theta to 2 theta through this operation.
Mm-hmm.
All right, so how is that an amplitude amplification?
Let's see. So let's see. Yeah, I think I see what you mean. Yeah, so amplitude has decreased.
Yeah.
But the thing is, let's see. Right. The important, clearly I made a mistake somewhere. I think the mass is still correct, but what is important is that if you apply this composition, then it rotates things in this two-dimensional subspace. So you could imagine, actually, yeah, that is not quite right. So I'm thinking maybe I have exchanged sine theta and cosine theta, but maybe I'll just look into this and yeah.
So
my suspicion is that I changed the sine and cosine, but
so basically the scheme is designed to bring the state vector closer and closer to the direction of the psi axis. Yeah.
Right, that's right. Yeah, whatever you desire. It's yeah. Okay, so I think I made a mistake. So I believe, yeah. Okay, so the reason why I think so is because down the road I will talk about the oblivious amplitude amplification, and I know for a fact that this is the correct statement. And yeah, here I get sine. So yeah, my apologies. Thank you for pointing this out. This is sine, and this is cosine. Yeah, good. Yeah, I believe this is correct, but in the next lecture, let me just make sure that everything is correct and notify everyone. Okay, so right. In the beginning, even if you have a small overlap, you can boost the amplitude. And so that's what the amplitude amplification is about. Okay, here's an interesting quiz that you might want to solve. So the question is, can you actually prepare this state psi exactly? And if you think about it, if theta happens to be a pi divided by some integer n, then the answer is obviously yes, because you can then, well, maybe, yeah, pi divided by 2n, and then you apply this n minus 1 times, and then you get an angle of pi over 2, and sine pi over 2, that's 1. So then clearly the answer is yes. But what would you do if you have a general angle theta? So this is the main question. Any guesses? So I'm asking this question because this is somewhat related to how you can boost the success probability to exactly 1. And there's a very like well-known trick, but somehow this is not like written down. This is like written in papers as a side note, but it's not like openly discussed in like a standard textbook. So I just wanted to tell you how this works. So the idea is that you artificially decrease your success probability. So remember, our setup was that you have this 0 state, which is the sine theta psi plus cosine theta psi in psi perpendicular. And the idea is the following. So this is our premise. And what do we have? We had I minus that, and I minus 2 that. And what we can simply do is that we can introduce R0 tilde, which is identity minus 2 the same state, same all zero state, but you have one extra qubit, again in the zero state. And you also have a slightly modified version of R psi, which is this is a tensor product of the psi state and some state on a single qubit. Let's call it as phi. Okay. And the initial state is simply psi theta prime psi tilde plus cosine theta prime psi tilde, and that, where we define psi tilde to be psi tensor phi. Okay, and the thing is, you can verify that sine theta prime is actually equal to sine theta. Let's see. Times the overlap of this phi state with the zero state. Okay, so the basic idea is that, let's say theta is an arbitrary real number, then you find the closest n such that theta is, let's see. So given theta, find the smallest n such that this is less or equal to theta. Yeah, so this is what you do. And then what you can do is that you can simply tune this, you can just choose this arbitrary state phi, such that sine pi over divided by 2n is equal to sine theta times the overlap. Okay, so the trick is very simple. You just simply redefine redefine your reflection, and you can do this very easily because you have simply changed your state by appending a single qubit state. And we can talk more about this if you're interested later, but it turns out that the cost of implementing this R tilde psi is not too different from implementing the cost of R psi. So basically, even though in the textbook version, you only talk about increasing the amplitude using this standard technique, you can simply modify this R psi to amplitude to amplify the amplitude to exactly 1. Okay, so that's just a general fact about quantum computing, but unfortunately, amplitude amplification is not exactly what we want, because in amplitude amplification, we can prepare a specific state that we want, given an ability to tell to apply a phase to that particular state. But in Oblivious amplitude amplification, let's see. Okay, so this is not written in a very nice way. So what I meant is that in the Oblivious, what we actually want is that we want an ability to apply a specific unitary to an arbitrary state instead of preparing an arbitrary quantum state. And that's what the Oblivious amplitude amplification is trying to achieve. And the basic setup is very similar to the amplitude amplification. So again, I have messed up the sine and cosine. So this should be sine theta and cosine theta. So what you sort of assume is this. So you have some unitary such that if you apply that unitary to this state, arbitrary quantum state and this extra register, then you apply some desired operation to this particular arbitrary quantum state. And that may succeed with some probability, sine squared theta, but sometimes it'll fail. But when you succeed, you will know that you succeeded because by measuring this extra register B, if you measure 0, then you know you've succeeded. And if you measure something else, like 1, then you will know that you had failed. Okay. And given this, the goal is to actually implement this unitary transformations. You begin with an arbitrary state and apply V of psi. So why is this relevant? It's because this is precisely the form that we had in this discussion about the linear combination of unitary. So in the linear combination of unitary, what we had was the following. So suppose you have this e to the minus I t I h t. Then what you did was that you first did a Taylor expansion of this thing into a linear combination of unitary. And then from that, you've built the select operation. And you've also built the prepare operation. And after applying this prepare, select, prepare dagger, apply to psi and an arbitrary state 0, arbitrary state psi and a fixed state 0. And if you measure this extra register in the basis that includes the all 0 state, then this turned out to be exactly equal to alpha p applied to an arbitrary state. And this is exactly equivalent to saying that this is actually equal to this state plus some, let's call this a junk state, where if you compute the inner product between this 0 state and junk, and this is exactly equal to 0. Okay, so we have already set ourselves up so that we can actually already implement a operation of this form. So Oblivious amplitude amplification is it was a technique that was developed to somehow boost this operation to an actual with a probability that is arbitrarily close to 1. And the math behind the Oblivious amplitude amplification is slightly more complicated, but what it does is very similar to the Oblivious amplitude amplification. So I won't go into details on how this actually works, but I think it'll be already interesting to understand what the statement is about. So what it does is the following. So first we define this operator S. It consists of U and R and U dagger and R. So what is U? U is this operation that we already discussed. So it's an operation that if we apply this state psi tends to 0, then with some probability, it implements the desired operation, but with some probability, it also fails to implement this desired operation. And one concrete example of that would be was this Hamiltonian simulation based on Taylor expansion. Okay, so that was U. What is this other thing R? It's simply a reflection operator. So what it does is that it looks at this extra register, and if it's 0, then it applies a phase. I guess the sign is okay. So I guess if you look at that, and if it's 0, then it doesn't apply a phase, and otherwise it does apply a phase. Anyway, up to a global phase, you could have also said that if you're in that particular state, you apply a phase, and otherwise you don't. So both of those operations are something that you can straightforwardly implement, because we already have shown how to implement that, at least for certain approaches to Hamiltonian simulation. And R, I guess I haven't told you, but believe me, this is has a very minor cost compared to the implementation of U. And if we simply iterate this S operations many times, you can simply boost this probability arbitrarily. So if you don't apply anything, you're in this original state, sine theta applied to this v psi, but if you apply this L times, you can increase this angle. And of course, if 2L plus L1 times theta is exactly equal to pi over 2, then this is exactly equal to v psi plus, plus 0. Well, actually, it's just that. So we can indeed deterministically apply the desired operation. And this is why I asked you about this quiz a couple of slides ago. So in the quiz I asked, so in the amplitude amplification, we can boost the amplitude, but only if the angle associated to that amplitude is a pi over 2 divided by some integer. But if that's not the case, that's also okay, because we can simply append a single qubit to drop the probability a little bit, so that the amplitude is associated to an actual pi over 2 divided by an actual integer. And we can apply the same trick here. So theta, this is just a arbitrary number that is given to us by, once you find a construction for U, then from that construction, you can often compute this value of theta. So once you do that, what you would do is that you simply add another single qubit to make the new theta be a pi over 2 divided by an integer. And then you can apply the Oblivious amplitude amplification to boost the probability exactly equal to 1. Okay, so are there any questions so far?
Yeah, okay. So if I want to get a very concrete handle on all of these schemes that you mentioned in the context of one specific Hamiltonian, then what would be that ideal Hamiltonian to practice with? Would that be the 1D Hubbard model, or maybe some other good model?
Let's see. I would say the most difficult part lies in actually doing the Taylor expansion. So whatever Hamiltonian that you're comfortable doing the Taylor expansion up to some order. But in some sense, like by the more modern methods, these difficulties are like almost all gone, because the best approach is right now, you don't the select and the prepare operations. The better approach is they don't encode the Taylor expansions. They just directly encode the information about the Hamiltonian. So for example, yeah, I mean, I guess we had this Ising model example. So if we were to do this for, if we were to apply the Taylor expansion method to this, then we would need to Taylor expand this thing. And then we're going to need to construct, select, and prepare based on that. But for the more modern methods, you simply choose select and prepare, so that select would be yeah. Actually, now that I think about it, I already talked about this, but maybe in a misleading way. So all you need to do in the more modern method is just yeah, just having a uniform superposition. Yeah, so in some sense, like actually doing the Taylor expansion, it's it maybe it wouldn't hurt for practice, but those methods are not going to be the best ones anyway.
Okay.
And can I let me just say that so there was a question in the last lecture about select and prepare, and I've shown examples of select and prepare for this kind of Hamiltonian, zi plus 1 and xi plus 1. And technically speaking, the select and prepare I showed were not correct, because I didn't actually Taylor expand this thing. In my mind, what I was thinking about the more modern methods. So they're select and prepare for more modern methods. And if I use those methods, the select and prepare that I showed you would have been correct, but just wanted to mention that. I should have Taylor expanded that when I answered that question.
Okay, thank you.
Yeah, okay, good. Okay, so now we can put everything together, because now we really do have everything. So I've shown you how to apply a linear combination of unitary operation by using select and prepare. And I've also shown you how to boost the probability. Okay. So if you do all this analysis, at the end of the day, the total cost scales as follows. So the important parameters, as I mentioned maybe a week ago, are three things. One is n, it's the number of qubits. The other is t, this is the simulation time. So how long the t is for e to the minus IHT. And the other thing is epsilon, which is the approximation error. And it turns out that this LC method, it's really nice in the sense that the simulation time, it goes almost linearly with the actual time. So as expected. And the precision it goes almost logarithmically, actually slightly better. So it's also like nearly optimal in that sense. And to get a reasonable gate code estimate, all you need to do is to simply multiply the cost of implementing the select and prepare subroutines. So the way this works, the way this algorithm works at the high level is basically applying this S operation over and over again. So you apply this UR, U dagger R, UR, U dagger R, UR, U dagger R, and R is just a very simple operation. And U was the operation that involved select and prepare. So because the algorithm has this such a very simple structure, all you really need to do is really quantify the cost of the select and prepare. So I've already told you very briefly about the cost of the select. And as I said, the naive approach that I've shown you, it scales as n log n. You have n because you could break down this entire circuit that I've shown to you into n different stages, and there's log n because if you account for all the costs that you need for this single stage, that cost ends up being like roughly log n. So that's where this cost is coming from. But a smarter approach can get down to order n. And I would say the state-of-the-art approach, which was due to Low, Khrushchev, and Schaeffer, can actually achieve a sublinear scaling in n for the T-gates, which are the most expensive ones. But the price you have to pay is that you need more and more qubits. So there are faster approaches, but probably those will be implemented in the far future, not in the very near term. And what about the prepare? So this question of synthesizing an arbitrary quantum state is a very often asked question in quantum computing. And these folks, Shende, Bullock, and Markov, they showed a method to do that. And it scales, again, almost linearly with n. And then, unfortunately, this log 1 over epsilon, you might think that it's not a big deal, but this log 1 over epsilon is actually coming from this rotation, like a arbitrary single qubit rotation. So that actually is a significant cost because a single qubit arbitrary angle rotation that costs roughly 100 T-gates, and each T-gate is far more expensive than clip-rate. So even though complexity theoretically this may seem fine, that this is what's kind of a problem in practically speaking. And then there was a very nice paper by Babush et al. From the Google folks who managed to actually separate out this log 1 over epsilon factor. And the constant in front of this n is actually pretty modest. It's like 4 or something, although, yeah, so it's very nice. And then again, now we have a slightly more flexible and better approach by these folks. Again, you can achieve sublinear scaling in n for T-gates, but again, you'll need more qubits to actually implement their method if you want to reduce the T-gates further. Okay, so I think the important lessons from these LCU methods is that in quantum computing, you can actually play with non-unitary operators, and that can be actually beneficial in designing algorithms. And although the LCU in the form that I've told you is not optimal, there are better ways of doing what I've said, what I've told you today. I think it is conceptually pretty nice. All you do is that you have this Hamilton, you have a time evolution. You just do the Taylor expansion. And that gives rise to select and prepare operations. And if you look into the Hamiltonian simulation algorithm, they're basically just applying select and prepare and their inverses like repeatedly. That's really all you're doing. So it has this nice benefit of having a more modular structure in the simulation algorithm. And also raised the question of like, what is the limit of applying these non-unitary operators in quantum computing? And are they actually useful? So, and these kinds of questions led to the development called cubitization and its generalizations, which I will discuss in the remaining lectures. Okay, so that's it for today. Thank you.
Thank you. So we are open for some questions, clarification, demands, or whatever else you might have in mind. Yeah, I have a kind of a very general question. There are all these wonderful schemes for improving the efficiency of the quantum computation or Hamiltonian simulation. And I think rather than waiting around for the big scale quantum computers to at our doorstep and we put these algorithms on the quantum computer, is it possible to use some of these ideas in doing some other stuff with existing method, maybe doing calculations on a classical computer or even doing some analytical calculations?
Oh, I see.
I mean, these ideas are
There,
good to be just to be played on a quantum computer only.
right. So there was some interesting work by Ewan Tang. This is not about Hamiltonian simulation, but, and I will probably not talk about this in this course, but there is this algorithm called HHL algorithm, which basically solves linear systems of linear equation on a quantum computer. Basically, you have ax equals b, and you want to solve x. And oh, okay, so it's not like she gave a classical version of that, but there are quantum machine learning algorithms which are based on this subroutine, and which at the time when people developed that, these algorithms were exponentially faster than the known classical algorithms. But then Ewan Tang showed that these methods can be actually, well, it's not like you can actually implement those on the classical computers, but there are methods, classical methods, which are exponentially faster than the older classical methods, which are inspired by these quantum developments. So there seems to be some developments in this direction as well, but maybe not Hamiltonian simulation yet.
Yeah, it doesn't really have to be like a quantum problem per se. I mean,
Right.
as long as these ideas become useful in some other context, that will be great to know.
Right. Yeah.
Okay.